Good morning, all of you. Today I am going to make an audio recording for visually impaired student of Organic Chemistry book of Dr. J.M. Sagal. Name of the chapter is Stereochemistry of Organic Compound. Introduction. The molecular structure of compound play a very important role in the study of organic chemistry. During this study, one come across many instances where a given molecular formula represent two or more compound having different properties. This is evidently due to some difference in the molecular structure of these compound. Such compound which have the same molecular formula but different properties are known as isomers, and the phenomena is known as isomerism. Isomerism. The concept of isomerism is an important feature of the study of organic compound. It relates to the existence of different compounds which have the same molecular formula but different properties. Such compounds are called isomers. Iso is equals to same, mers is equals to part. The difference in the property of isomer is due to the difference in the relative arrangement of atom in their molecules. There are two types of isomers. First, structural isomers. Second, space or stereoisomerism. Structural isomerism. This is the type of isomerism which is due to the difference in the arrangement of atoms within the molecule having the same molecular formula. The student is already familiar with the various types of structural isomerism. However, we shall present here a brief review for the sake of recapitulation. First, chain or nuclear isomerism. This is a kind of isomerism which arises when the compound having the same molecular formula differ only in the arrangement of carbon atom in a chain. Thus, normal butane and isobutane having the same molecular formula C4H10 represent two chain isomers, N-butane and isobutane. Similarly, there are three chain isomers having the molecular formula C5H12. These are N-pentane, isopentane, neopentane. Second, position isomerism. If two or more compounds with the same molecular formula have different position occupied by a characteristic atom or group attached to a carbon, position isomerism is said to exist. N-propyl chloride and isopropyl chloride afford an outstanding example of this type of isomerism. Both these compounds have the same molecular formula C3H7Cl, the same carbon skeleton, but differ from each other in the position of attachment of chlorine atom. N-propyl chloride, isopropyl chloride. Similarly, there are two butenes C4H8 which differ in the position of double bond in the molecule. But 1 in, but 2 in. Third, functional isomerism. This type of isomerism is due to the presence of different functional groups in compound having the same molecular formula. For instance, C2H6O represent two compounds, ethyl alcohol, dimethyl ether. These two compounds have entirely different physical and chemical properties because of the presence of different characteristics group. Acetone and propanoaldehyde C3H6O represent another pair of compound exhibits functional isomerism. Metamerism. This type of isomerism is due to the difference in the redistribution of carbon atom on either side of functional group in compounds having the same molecular formula. For instance, diethyl ether and methyl propyl ether represent a pair of metamers having the molecular formula C4H10O. Diethyl ether, methyl propyl ether. Ethyl ketone and methyl propyl ketone having the molecular formula C5H10O furnish another case of metamers. C3CH2 C double bond O CH2CH3 is diethyl ketone. Second is CH3 C double bond O CH2 single bond CH2 single bond CH3. It is methyl propyl ketone. Fifth, ring chain isomerism. This is a type of isomerism in which two compounds having the same molecular formula have open chain and ring structures respectively. For example, propene and cyclopropane having the molecular formula C3H6 afford a simple example of ring chain isomerism. CH3 single bond CH double bond CH2 is propene, and CH2 single bond CH2 single bond CH2 is cyclopropene. Similarly, but1-ine and cyclobutane are also ring chain isomerism of each other. 6 is tautomerism. This is a special type of functional isomerism where the isomer exists simultaneously in dynamic equilibrium with each other. The isomers which are involved in equilibrium are called tautomers. The structure of tautomers generally differ from each other in point of attachment of one of the atom in the molecule. In ketoenol tautomerism, which is the most important type of tautomerism, the tautomers differ from each other in the point of attachment of a hydrogen. Thus, acetylacetone exists as a tautomeric mixture of two forms, the keto form and the enol form, which differ in the point of attachment of hydrogen as shown below. CH3 C double bond O, single bond CH2, single bond C double bond O, single bond CH3 is a keto form of acetone. Equilibrium sign CH3 single bond C OH double bond CH single bond C double bond O single bond CH3 is the anolic form of acetylacetone. Similarly, ethyl acetoacetate exists as a mixture of keto and enolic form. CH3 single bond C double bond O single bond CH2 single bond C double bond O single bond OC2H5. This is a keto form. Equilibrium sign CH3 single bond C single bond OH double bond CH single bond C double bond O single bond OC2H5 is the anolic form. Tautomerism versus resonance. It will be quite appropriate at this stage to distinguish between the phenomena of tautomerism and resonance. It may be noted that first, tautomerism is marked by the existence of distinct structure which differ mainly in the point of attachment of one atom in the molecule. Second, the tautomers are distinct compounds which are actually known to exist and which may even be isolated in certain cases. On the other hand, in resonance, contributing structure do not exist as such. They are written only to have an idea of the structure of resonance hybrid, as this structure cannot be represented in terms of the valence bond method of the representation. Stereoisomerism. This is the type of isomerism which arises due to the difference in the arrangement of atom in space. Its study is known as stereochemistry. In this unit, we shall discuss the important aspect of stereoisomerism. The isomeric compound which differ from each other only in the relative arrangement of atom in space, but resemble one another with respect to which atom are linked to which other atom are called stereoisomers, and the phenomena is known as stereoisomerism. There are three types of stereoisomerism. First, optical isomerism. Second, geometrical isomerism. Third, conformational isomerism. Before proceeding further, it may be pointed out that the different structure of conformational isomerism of a substance are non-superimposable on one another but are easily interconverted into each other by rotation around single bond. In contrast to this, the different structure of optical or geometrical isomerism are non-superimposable on one another, and at the same time they cannot be interconverted except by breaking and making of bond. For this reason, optical and geometrical isomerism are also collectively known as configurational isomerism, while conformational isomers of a substance exist only as a mixture of different forms. The configurational isomers can be prepared as distinctly individual substances. For difference between conformation and configuration, please refer to section 2.20. We shall now discuss the different type of stereoisomerism, starting with optical isomerism. Optical isomers. This is a type of stereoisomerism in which the isomeric compounds resemble one another in their chemical reaction and most of the physical properties but differ in their effect on polarized light. We shall now first review some fundamental terms concerning optical isomerism and then discuss other features of optical isomerism. First, tetrahedral concept of carbon. It is well known that in methane and all other compound having a carbon bonded to one another atom or group by single bond, the four bonds of carbon are directed towards the four corners of tetrahedron. The tetrahedral concept of carbon is put forward by Liebel and Van 't Hoff is very helpful in understanding the phenomena of optical isomers. A representation of the tetrahedral carbon atom is shown in figure 2.1a by molecular model and in figure 2.1 by wedge formula. It should be noted that by convention, the wedge represents the bonding pointing towards the observer out of the plane of the paper. The hatch line or dash line represent the bond behind the plane of the paper. The normal lines shows the bond in the plane of the paper. Second is polarized light. An ordinary ray of light consists of electromagnetic wave of various wavelength, and its vibration take place in all plane at right angle to the direction in which it travels. A ray of light which consists of wave having only one wavelength is known as monochromatic light. Even such a ray have its vibration in all planes. However, if the ray of monochromatic light such as yellow light from a sodium flame is passed through a nickel prism, a special prism made from calcite, which is a particular crystalline form of calcium carbonate, the wave motion of emergent light is restricted to only one plane. Light whose vibration take place in only one plane is known as plane polarized light or just polarized light. The plane along which vibration take place is known as plane of polarization, and the nickel prism used for polarizing the light is known as polarizer. Source of light is a bulb, then unpolarized light, then place a polarizer, and then we get polarized light. Third is optical activity. There are certain substances which can rotate the plane of polarized light. For instance, when polarized light vibrating in certain planes is passed through cane sugar solution, the light which emerge out vibrate in different planes. Such substances which can rotate the plane of polarized light are said to be optically active, and the property is known as optical activity. The substance which rotate the plane of polarized light towards the right are termed as dextrorotatory plus, while those which rotate the left are called levorotatory minus. The instrument used for measuring the angle of rotation, denoted as alpha of plane polarized light, is known as polarimeter. The angle of rotation through which plane of polarized light is rotated by an optically active substance depend upon many factors, which are: first, nature of compound; second, length of liquid column through which the light passes; third, concentration of solution and nature of the solvent in case of solid substance only; fourth is temperature; and fifth is wavelength of light used. Fourth is specific rotation. In order to compare the rotatory power of different substances, optical activity is expressed as specific notation: alpha bracket d and t. It is the angle of rotation of the plane polarized light produced by a tube 1 decimeter in length filled with a solution having 1 gram of the substance per ml of the solution at the temperature T, using light of wavelength 5893 angstrom from sodium vapor lamp. This light is called D line of sodium. Specific rotation is generally calculated from the equation alpha is equals to observed angle of the rotation divided by L into D, where D represents the weight in grams of solute in 1 ml of solution or density of the substance if it's liquid, and L is the length in decimeter of the tube filled with the sample. For instance, the specific rotation of cane sugar solution at 293 Kelvin is plus 66.5 degree D293. Fifth is elements of symmetry. The phenomena of optical activity is essentially related to lack of symmetry in molecular structure. A simple method to decide whether a molecule is symmetrical or not involves three criteria of symmetry known as element of symmetry. An element of symmetry may be defined as plane, line or point with respect to which the structure possesses a definite symmetry. There are three elements of symmetry as discussed below. First, plane of symmetry. It is an imaginary plane passing through an object or the structure which divide the object or structure into two halves such that one half is the mirror image of the other. For example, a beaker has a plane of symmetry as shown below in figure 2.3. Similarly, the molecule of propanoic acid has a plane of symmetry as shown in figure 2.3b. In the study of optical isomerism, the plane of symmetry may be shown simply with the help of three-dimensional formula or many conventionally by using plane formula as shown in figure 2.4a and 2.4b for the molecule of 2,2-dibromobutane. Human hand is most perfect example of an object having no plane of symmetry. 2-chlorobutane, lactic acid and alanine are some example of molecules which do not have any plane of symmetry. Second is center of symmetry. It is an imaginary point within a molecule at which all the straight lines joining identical points in a molecule cross each other. For example, the center of symmetry in a molecule of 2,4-dimethyl cyclobutane 1,3-dicarboxylic acid is shown below in figure 2.5. It may be noted that a structure can have more than one plane of symmetry, but no structure can have more than one center of symmetry. Third is axis of symmetry. It is an imaginary line passing through the molecule so that when the molecule is rotated about this line, exactly similar geometrical arrangement appears more than once in one complete revolution. It means in rotation through 360 degree, if the identical arrangement appears twice, in one complete revolution after every 180 degree, the axis is called two-fold axis of symmetry denoted as C2 axis. If the similar arrangement appears thrice, it is three-fold axis of symmetry and so on. For example, trans 1,2-dibromocyclopropene possesses a C2 axis of symmetry in the plane of ring which bisects the bond between carbon atom 1 and 2 and intersect the carbon atom 3 as shown in figure 2.6. When rotated around this axis, the same arrangement appears after every 180 degree. Alternating axis of symmetry or rotation reflection axis. This is another element of symmetry which is rarely used. A molecule is said to have an n-fold alternating axis of symmetry if rotation by an angle of 360 by n about the axis followed by reflection in plane perpendicular to that axis gives a molecule which cannot be distinguished from the original molecule. For example, 1,3-diethyl 2,4-dimethyl cyclobutane possesses a two-fold axis of symmetry is shown below. If a molecule A is rotated by the angle of 180 degree, it means 360 degree by 2 about the axis S2 which passes through the center of ring, it gives a molecule B. The reflection of B in the plane perpendicular to the axis gives the original molecule A. It may be noted that a one-fold alternating axis of symmetry corresponds to a plane of symmetry while a two-fold alternating axis of symmetry corresponds to the center of symmetry. Sixth is molecular chirality. Chiral molecule and achiral structure. First is chiral structure. A structure or object is said to be chiral or dissymmetric if it is not superimposable on its mirror image. Such a structure does not have either a plane or a center of symmetry. The most perfect example of a chiral object is human hand. It does not have any plane of symmetry and cannot be superimposed on its mirror image. If you hold your left hand up to a mirror, the image looks like a right hand, but if you try to superimpose one hand over the other, both palms down, you cannot do it. Figure 2.7. Similarly, a right-handed glove and a left-handed glove are chiral objects. A very large number of organic molecules such as 2-chlorobutane and lactic acid are known to have chiral structure and they are non-superimposable on their mirror images. The substances having chiral structure are said to possess the property of chirality. It should be noted that chirality is the property of complete object or structure and not of its part. It may also be noted that even though there are three kinds of element of symmetry, chirality is primarily related to lack of plane of symmetry and the center of symmetry. Second is achiral structure. A structure of or object which has a plane of symmetry and is superimposable on its mirror image is known as achiral or symmetrical. Such a structure always possesses a plane of symmetry or a center of symmetry. For example, the letter A and the button on your shirt represent achiral symmetry or object. It can be easily seen that each of these have a plane of symmetry and it is superimposable on its mirror image, figure 2.8. Methane and carbon tetrachloride are perfect example of molecule having a chiral structure and they are superimposable on their respective mirror image. Two objects are said to be superimposable if when placed on one upon the other, their corresponding pair parts lie together. Two objects that are like mirror images of each other may be either superimposable or non-superimposable. For example, two notebooks of same size having mirror image relationship are superimposable. The term chiral, based upon the Greek word chia, which means hand, was first introduced by the Chen, England, and Prelog in 1964. Thus, chilarity means handedness. Handedness. It means the relationship which exists between the left and right hands. In this recent year, the term chiral and chirality have almost completely replaced on the old term dissymmetry and disymmetry respectively. Third is origin of chirality in organic compound. Most of the organic compound which are chiral in nature owe their chirality to presence of a compound atom bonded to four different groups. Such a carbon is termed as chiral carbon or chiral center or stereogenic center or stereocenter, earlier known as asymmetric carbon. A stereogenic center or chiral carbon is a carbon atom which is bounded to four different monovalent atom or groups such as a CABCD. There can be two different tetrahedral modes for CABCD which differ in the spatial arrangement of various groups attached to the carbon as shown in figure 2.9. Each of the two models is related to other like an object to its mirror image and one cannot be superimposed on the other no matter how we turn or twist them. Each of these models therefore represent a chiral structure. Similarly, we can have two non-superimposable mirror image structure for any compound which contain a stereogenic center or chiral center. For example, lactic acid and 2-methyl-1-butanol are chiral molecules since each of them consists a chiral center. The one marked asterisk, figure 2.2, figure 2.10. It must be emphasized, however, that certain molecule may contain more than one stereogenic or chiral center and still they may be achiral or non-disymmetric. For instance, 2,3-dichlorobutane CH3 CH asterisk Cl single bond CH asterisk Cl single bond CH3 which has two chiral center, those marked asterisk exist in many isomeric form, one of which is not chiral because it has a plane of symmetry as shown below. Chiral molecules not containing any chiral carbon. There are certain molecules known to exist which are chiral even though they do not contain any chiral carbon. For example, allenes represent a well-known class of such compound as illustrated below. It may be seen by molecular models that chirality is 2,3-pentyne arise due to the fact that the two groups singly bonded to one of the and carbon atom of allene system are in different plane than the two groups singly bonded to the other and carbon of allene system. Substituted diphenyl constitute another example of such compound which are chiral without containing any chiral carbon atom. The chirality is a system such compound arise due to the fact that the two benzene rings lie in different plane perpendicular to each other. Optical isomerism in enantiomerism. It have been observed that optically active substances always exist in two or more isomeric forms which differ with respect to their optical activity or their reaction on plane polarized light. As already stated, the isomers which resemble on one another is their classical chemical reaction and most of the physical properties but differ in their effect on polarized light are called optical isomers and the phenomena is known as optical isomerism. There are two main types of optical isomerism. These are first enantiomerism and second is diastereomerism. We shall now discuss these two types starting with enantiomer. First is enantiomerism. It is simplest kind of optical isomerism which was discovered by Pasteur in 1848 as a result of his hard work on the salt of tartaric acid. He observed that optically inactive sodium ammonium tartrate consisted of a mixture of two distinct types of crystal. These two types of crystal were not superimposable on each other, although their shapes were like mirror image of each other. The relationship between the two types of crystal may be compared to that between a pair of right and left-handed gloves. Pasteur separated the two types of crystal from the original sample with the help of magnifying lens and a pair of tweezers. Unlike the original optical inactive sample, each type of crystal was found to be optical active in its aqueous solution. Moreover, the specific rotation of the solution of one type of crystal was found to be equal but of opposite sign to that of the solution of second type of crystal. Considering the fact that difference in optical rotation was observed in the solution where the solute exists in the form of simple molecule, Pasteur proposed that the molecule constituting the two types of crystal were also non-superimposable mirror image of each other. Such isomers whose molecular structure are non-superimposable mirror image of each other and which rotate the plane polarized light equally by an opposite direction are known as enantiomer or enantiomorphous. The phenomena of mirror image isomerism are called enantiomerism. Since the mirror image isomer differ only in the spatial arrangement of atom, enantiomerism represents a type of stereoisomerism. Explanation of enantiomerism. The existence of mirror image isomer or enantiomerism were justified by Van 't Hoff on the basis of tetrahedral concept of carbon atom. Let us try to apply this concept to an imaginary compound of the type CABCD in which a carbon atom is attached to four different groups. Such a compound, which can be represented by two different tetrahedral models which differ in the spatial arrangement of various groups attached to the carbon atom. The two models are related to each other like an object and its mirror image, and one cannot be superimposed over the other no matter how we turn or twist them. These models represent two enantiomerism of the compound. For example, let us draw tetrahedral formula of enantiomeric form of substances such as lactic acid, CH3CH, OH, C double bond, C double oxygen H, and 2-methyl-1-butanol, which are known to exist enantiomerism. In each of these cases, we found that it is possible to construct two formula which are non-superimposable mirror image of each other, and as such they represent the different enantiomers. Figure 2.10 on page 2 by 10. It may be pointed out, however, that if compound containing a tetrahedral carbon atom does not have a four different group attached to this carbon, and then the molecule are superimposable on their mirror image. This is illustrated below with the help of bromochloromethane CH2Cl-Br. Such compounds do not exhibit enantiomerism because all their molecules are of same type. Second is fundamental condition for enantiomerism. It have been shown above the enantiomeric molecule are always non-superimposable mirror images of each other. The non-superimposibility of mirror image invariably arises due to the chiral nature of molecule. As already stated, a molecule is termed as chiral if it has no plane or center of symmetry and therefore non-superimposable on its mirror image. Chilarity is the most of the enantiomeric molecule is itself due to the presence of at least one chiral carbon in the molecule. For example, lactic acid and 2-methyl-1-butanol contain one chiral carbon atom and therefore exist as enantiomeric form as shown in figure 3.10 on page 3 by 10. At the same time, there can be molecules such as 2,3-pentadiene and substituted biphenyl such as 6,6-dinitrophenic acid, which do not contain any chiral carbon, but they still possess the property of chilarity and thus exhibits enantiomerism. It may be concluded, therefore, that chilarity, property of existing as non-superimposable mirror image, is a fundamental and only condition of enantiomerism. Third is characteristics of enantiomers. The important characteristics of the enantiomer of given substance are described below. First, they have identical physical properties such as melting point, boiling point, density, solubilities, refractive index. The only difference lies in the direction of rotation of plane polarized light, although even they have the magnitude of specific rotation is same. For example, the specific rotation of 2 enantiomer, 2-methyl 1-butanol are plus 576 degree and minus 5.76 degree respectively. Second is they have identical chemical properties except in the reaction with other optical active compound. For example, the ordinary chemical reaction of plus lactic acid are exactly like those of minus lactic acid. Moreover, there is no difference in the speed of such reaction. There may be difference, however, in the rate of reaction at which the two enantiomer react with some other optically active compound. For instance, the rate of esterification of plus lactic acid and plus secondary butyl alcohol, which is optically active, would be different from the rate of esterification of minus lactic acid with the same alcohol. Third is they have different biological properties. In contrast to physical and usual chemical properties, enantiomers are quite different in their biological properties. For example, plus sugar plays an important role in animal metabolism, whereas minus sugar is not metabolized at all. Similarly, plus tartaric acid is readily consumed by the mold Penicillium glacium, while minus tartaric acid is not. Fourth, when equal quantities of enantiomer are mixed together, it results in the formation of an optically inactive form called racemic modification or racemic mixture or racemate. The racemic modification is distinguished by using the prefix plus minus before the name of compound. For example, if equal quantities of plus lactic acid and minus lactic acid are mixed with each other, we get racemic or plus minus lactic acid, which is optically inactive. Fourth is enantiomerism and optical activity. We have just learned that the fundamental condition for the phenomena of enantiomers is the chiral nature of molecule, and the fundamental difference between enantiomer of the given substance is the direction of optical rotation. Let us now examine as to what structural feature give rise to optical activity and how is to related to phenomena of enantiomerism. A single individual molecule of nearly every substance can cause some rotation of the plane polarized light when a beam of such light passes through the molecule. The direction and extent of rotation caused by a particular molecule depend upon its orientation in beam of light. But in actual practice, it is not possible to have with us only a single molecule of substance, even a very small sample of substance being made up of very large number of molecules distributed at random. Therefore, what happens in most of the cases is that for every molecule that rotates the plane polarized light, there is another identical molecule oriented as the mirror image of the first, which exactly cancel its effect. As such, no optional rotation can be observed. This means that optical inactivity of substance is basically due to the random distribution of identical molecules, which can serve as the mirror image of each other. But in the case of chiral molecule, the mirror image of any one molecule is not another identical molecule, rather it is different isomeric molecule. Now if we take a pure sample consisting of single enantiomer, no molecule can serve as the mirror image of another. As a result, there cannot be exact cancellation of rotation and as optical activity is observed. Thus a given sample of a substance can exist optical activity only if its constituent molecules are not superimposable mirror image of one another. In other words, chilarity non-superimposability of mirror image is also the fundamental and sufficient condition for optical activity. Representation of stereoisomerism. First is flying wedge formula. We have so far used the molecular model and three-dimensional tetrahedral formula to represent the stereoisomers. The tetrahedral formula can also be drawn in somewhat different but more convenient way known as flying wedge formula. For drawing these formula, the molecule is oriented in space in such a way that two bonds to the stereo center pointed towards the observer, while the other two bonds are directed away from the observer. The bonds pointing towards the observer are represented by wedge drawn horizontally, which may or may not be drawn along the straight line. The bond pointing away from the observer are represented by hedge or dotted lines drawn vertically. For example, the molecular model tetrahedral formula and flying wedge formula of one of the enantiomer of lactic acid may be shown as follows. Similarly, the three kinds of representation of other enantiomer of lactic acid can be shown. A tetrahedral and flying wedge formula of enantiomer of 2-butanol are given below. Second is planar representation of three-dimensional formula, Fischer projection formula. The use of molecular model is no doubt the most suitable method of showing the spatial orientation of atom constituting of the molecule, but it is not very convenient to represent the formula of compounds on paper. Therefore, a simple although not foolproof method was introduced by Emil Fischer 1891 for projecting three-dimensional formula of chiral molecule on plane surface. The planar representation are called Fischer projection formula. Procedure for writing Fischer projection. For writing the projection formula, the following procedure is adopted. First is the chiral molecule is viewed in such a way that two groups bound to chiral carbon point towards the observer while the other two groups pointed away from the observer. Second is the various groups attached to the chiral carbon are then projected to the plane of paper in form of a cross so that horizontal lines represent bonds pointing towards the observer while the vertical line represent bonds pointing away from the observer. If the chiral molecule contains two or more carbon, each carbon is considered separately as described above. Third is the vertical part of the projection formula should represent so far as possible the longest chain of the carbon atom in the molecule, with the carbon atom to be numbered as 1 according to IUPAC system being written at the top. Fourth is the chiral carbon atom is not written at all. While writing the projection formula, it is taken for granted that the chiral carbon is located where the horizontal and vertical line cross each other. For instance, the projection formula of the two enantiomer of lactic acid may be represented as shown ahead. Molecular model and Fischer projection formula of two enantiomer of lactic acid. It should be noted that more than one Fischer projection can be written for some compound depending upon which bonds are shown horizontally and which bonds are drawn vertically. It is therefore necessary to test whether the given Fischer projection represents the same stereoisomer of a compound or not. This can be done by using the following rule. First, a Fischer projection may be imagined to be rotated from end to end without lifting it from the plane of paper. Rotation by 180 degree in the plane of paper does not bring about any change in the configuration. For example, if the projection first of lactic acid is rotated through 180 degree in the plane of paper, it gives projection second. Since no change of configuration takes place in rotation by 180 degree, projection first and second represent the same stereoisomer of lactic acid. But rotation by 90 degree or 270 degree leads to inversion of the configuration. It means change one configuration into its mirror image so that the new configuration represents the enantiomer of original compound. Second is, if position of two group or atom above the chiral carbon atom are interchanged, it also leads to inversion of configuration. But if we carry out two such interchange, the configuration remain unaltered. It is quite evident from the above that one interchange is equivalent to rotation by 90 degree or 270 degree, while two interchange are equivalent to the rotation by 180 degree. Chiral and achiral molecule with two stereogenic centers, diastereoisomerism. We have learned that a compound containing one stereogenic center exists in two stereoisomeric forms which are known as enantiomer of each other. What about compound containing two stereogenic center? Quite acceptedly, such compound can exist in more than two stereoisomeric form. To illustrate this statement, let us consider the case of 2,3-dichloropentane. which contain two stereogenic centers. Since the four different groups attached to one stereogenic center are not the same as those attached to the other, the two chiral carbon atoms are dissimilar from the other. There are as many as four stereoisomerisms, first, second, third, and fourth, possible for this compound. First and second is the one pair of enantiomer, and second and third and fourth is the second pair of enantiomer. Examination of formula first and second reveals that they are non-superimposable mirror image of each other and hence represent a pair of enantiomer. Similarly, third and fourth are also non-superimposable mirror image of each other and as such represent another pair of enantiomer. Let us now compare the formula first with formula second. It becomes immediately clear that the two formula have identical configuration about one chiral carbon C2 but mirror image configuration about the other chiral carbon C3. The net result is that the two forms are neither identical nor in mirror image of each other. Such stereoisomerism of substance which are not mirror image of each other are known as diastereomerism. In addition to formula first and third, formula 1 and 4, second and third, second and fourth also represent a pair of diastereomerism. Fischer projection formula and flying wedge representation of four stereoisomers of 2,3 dichloropentane are given below. 3-chloro-2-butanol afford another example of compound having two dissimilar chiral carbon atom which can exist in four stereoisomeric form as given below. It may be seen that structure 5th and 7th, 5th and 8th, 6th and 7th, 6th and 8 represent pair of diastereomerism. Characteristics of diastereomerism. The important characteristics of diastereomers are as follows. First, they show similar but not identical chemical properties. In the reaction of two diastereomers with a given reagent, the rate of reaction are generally different from each other. This is because diastereomers have different energies of activation for a particular reaction and therefore they react at different rates. Second is they have different physical properties such as melting point, boiling point, densities, solubilities and refractive index. Third is their specific rotation are also different from each other. In fact, some of the diastereomers may be even optically inactive. It should be noted that geometrical isomers are also diastereomers of each other but they are optically inactive. Fourth, on account of different physical properties, diastereomers can rather easily separated from each other by physical methods such as fractional crystallization, fractional distillation, chromatography, etc. Comparison of diastereomers and enantiomer. First is diastereomers are stereoisomers which do not have a mirror image relationship, whereas enantiomers are the stereoisomers which have a mirror image relationship. Second is diastereomers have different physical properties such as melting point, boiling point, solubility in a given solvent and density, whereas enantiomers have identical physical properties such as melting point, boiling point, solubility in given solvent and density. Third is diastereomers can be separated by fractional distillation, fractional crystallization and observation chromatography, whereas enantiomer cannot be separated by such method. Diastereomers may have optical rotation in some or opposite direction but to a different extent. In enantiomers, they have optical rotation in opposite direction but to the same extent. Diastereomers have identical chemical properties but different in the rate of reaction with optically active compound, whereas enantiomers have identical chemical properties except with other optical active compound. Hetero and stereoisomers. A special system of nomenclature is sometimes used for distinguish between diastereomers in which two of the atom or group attached to one stereogenic center are the same as the two atom or group attached to the other stereogenic center. This method is derived from the names of two diastereomeric carbohydrates, ethers in which two similar groups are on the same side and theros in which similar groups are on the opposite sides as shown below. Ethers and theros. If the two similar groups are on one same side in the Fischer projection formula of the similar molecule, the diastereomers is known as heteroisomer. If the two similar groups are on the opposite side in the projection formula of the molecule, the diastereomers is known as stereoisomers. For example, of the 4 isomer of 3-chloro-2-butanol, one pair of enantiomer is known as hetero, while the other pair of enantiomer, which are diastereomer of the first pair, is known as stereo as illustrated below. Hetero 3-chloro-2-butanol, one pair of enantiomer, and stereo 3-chloro-2-butanol, other pair of enantiomers. It may be seen that any one compound of one pair is diastereomer of any one compound of the other pair. The name hetero and stereo are derived from the names of two simple sugar heteros and stereos having the following configurations. Meso compound. Let us now consider a compound containing two similar chiral centers. It means having the same set of 4 different groups attached to each of the chiral carbon atom. A typical example of such a compound is provided by tartaric acid. In view of the fact that it has two chiral centers, one may accept the existence of 4 stereomers of this acid having the configuration 9, 10th, 11 and 12th. 9th and 10th pair of enantiomers and 11th and 12th superimposable mirror image represented only one compound. Formula 9th and 10th are non-superimposable mirror image of each other and therefore represent a pair of optically active enantiomer. Formula 11th and 12th again have a mirror image relationship. Close examination of these formula, however, shows that one of these structure may be superimposed on the other just by rotating it through 180 degrees within the plane of paper. These two formula therefore represent two superimposable mirror image molecules of the same compound. Further examination of formula 11th and 12th reveals that in spite of two chiral center in it, the molecule is achiral. This is because it has a plane of symmetry, one half of its molecule being mirror image of the other half. As such of the compound represented by formula 11th or 12th is optically inactive, such as in optically inactive compound whose molecules are not chiral even though they contain two chiral centers is known as meso compound. As explained above, the molecule of such compound are superimposable on their mirror image. Thus, tartaric acid exists in the 3 forms: minus tartaric acid, plus tartaric acid, formula 9th and 10th, and mesotartaric acid, formula 11th and 12th. Although optically inactive, the mesotartaric acid represent a diastereomers of minus and plus tartaric acid. Fischer projection formula and flying wedge formula of 3 stereoisomer of tartaric acid are given below. It should be noted that meso compounds are permanently inactive and are said to be internally compensated. This is because one half of the molecule cancel the rotation due to the other half. 2,3-dichlorobutane afford another example of a compound which contain 2 chiral carbon and exists in 3 form: 2 optically active form and 1 meso form. Number of possible stereomers in compound containing different number of chiral center. It may be stated that maximum possible number of stereomers of a molecule is 2n, where n is the number of chiral center in the molecule. Thus, the molecule having 1, 2, 3 chiral carbon atom exist in 2, 4, 8 stereoisomeric form respectively. But the actual number may be lesser than the maximum if some of the isomeric exist in the meso form. It is possible to predict the actual number of stereomers by simple calculation as explained below. First, when the molecule contains n stereogenic center, n may be odd or even number and the molecule has no plane of symmetry. Number of optically active isomer D and L form is equals to 2n. Number of meso form is equals to 0. Total number of isomer is equals to 2n plus 0 is equals to 2n. For example, 2,3-dichloropentane have two stereogenic center exist in the form of 2 k power 2 is equals to 4 optically active isomer as already shown on page 2 by 16. Second, when the molecule contain n stereogenic center where n is equals to an even number and the molecule has a plane of symmetry, number of optically active form is equals to 2n minus 1, number of mesoform is equals to 2n by 2 minus 1, total number of isomer is equals to 2 power n minus 1 plus 2 power n by 2 minus 1. For example, tartaric acid, 2 stereogenic center with a plane of symmetry exist as 2 power 2 minus 1 is equals to 2 optically active isomer and 2 power 2 divided by 2 minus 1 is equals to 2 power 0 is equals to 1 mesoform. Total number of isomers is equal to 2 plus 1 is equals to 3 already shown on page 2 by 17. Third, when a molecule contains n stereogenic center where n is equals to an odd number and the molecule may have a plane of symmetry, number of optical active form is equals to 2 power n minus 1 minus 2 power n minus 1 divided by 2. Number of mesoform is equals to 2 power n minus 1 divided by 2. Total number of isomer is equals to 2 power n minus 1 minus 2 power n minus 1 divided by 2 plus 2 power n minus 1 divided by 2 is equals to 2 power n minus 1. For example, pentane 2,3,4 trianol 3 stereogenic centers with a possible plane of symmetry exist as 2 power 3 minus 1 minus 2 power 3 minus 1 divided by 2 is equals to 2 power 2 minus 2 power 1 is equals to 2 optically active form. 2 power 3 minus 1 divided by 2 is equals to 2 power 1 is equals to 2 mesoform. Total number of isomer is equals to 2 plus 2 is equals to 4. These isomers are shown below. First is optically active, second is optically active, third is mesoform and fourth is also mesoform. It is possible to draw 4 more structure but each of these would be found to be superimposable on one or the other of the above structure as can be seen by rotation through 180 degree within the plane of the paper. Racemization. It has been stated earlier that an optically inactive mixture containing equal quantities of enantiomer of a substance is known as racemic mixture or racemate. It is denoted by using the prefix plus minus or DL or RS before the name of the compound. For example, a racemic mixture of lactic acid is denoted as plus minus lactic acid. Racemic mixture can be formed in one of the following 3 ways. First is synthesis of chiral compound from a chiral reactant. Please see section 3.14. Second is mixing of equal amount of 2 enantiomer already described, and third is racemization. We will now consider the process of racemization and its mechanism. First is racemization. The conversion of an optically active compound into a racemic mixture containing equal amount of original compound and its enantiomer is known as racemization. Racemization can be brought about by one of the following methods depending upon the nature of compound. First is by the action of heat. Quite often an optically active enantiomer changes from into a racemic mixture by the action of heat. For example, when plus tartaric acid is strongly heated with water, it converted into a mixture of racemic and mesotartaric acids. Second is by the action of chemical reagent. Racemization is also brought about by the presence of foreign substances, particularly acid and base, in the solution of an optically active substance. For example, addition of sodium hydroxide to plus or minus lactic acid leads to the formation of a racemic mixture. Third is auto-racemization. In some cases, racemization takes place by merely keeping the substance at room temperature for some time. This is known as auto-racemization. For example, any one of the enantiomer of dimethyl bromocyanate changes into a racemic mixture on standing at room temperature. Mechanism of racemization. . 。  . 。 . Different mechanisms have been developed for the racemization of different type of compound, but in majority of cases, racemization is believed to take place through the formation of some intermediate which is no longer chiral in nature as explained ahead. Acid catalyzed racemization of an optically active aldehyde or ketone in which the chiral carbon carries a hydrogen and is in alpha position with respect to the carbonyl group take place through enolization. It means the intermediate formation of an achiral enol by tautomeric change. The enolic form being unstable reverts to the chiral keto form, but in doing so it produces plus and minus enantiomer in equal quantities and thus racemization take place. This is shown ahead with the help of 3-methyl 2-pentanone. Irrespective of whether the starting compound is plus or minus 3-methyl 2-pentanone, the final product is a racemic mixture since both the enantiomer are formed in equal quantities. Base catalyzed racemization of minus lactic acid take place through the formation of an achiral carbanion as shown below. Minus enantiomer plus OH negative, equilibrium sign H2O positive, H2O plus loss of chilarity, equilibrium sign H2O plus enantiomer. The final product would be a racemic mixture whether we start with minus or plus enantiomer of the lactic acid. We will come across many examples of chemical reaction in the text such as SN1 reaction of the alkyl halide discussed in chapter 9 which are accompanied by complete on partial racemization. Partial racemization means that one enantiomer may be formed in larger amount than the other so that the mixture of the two will not be completely inactive. Internal and external compensation. First is internal compensation. It has been stated above the meso compound are optically inactive because their molecules are not chiral even though they contain two or more chiral centers. For example, it is clear from the structural formula of mesotartaric acid that the top half of the structure is the mirror image of the bottom half. As such, the optical activity due to the one chiral center is counterbalanced by the optical activity due to the other and the compound is optically inactive. The counterbalancing of optical activity of one half of the molecule by the other half is known as intercompensation and the molecule is said to be internally compensated, as internally compensated molecule is permanently inactive. Second is external compensation. In an equimolar mixture of two enantiomers, say plus and minus lactic acid, the molecule of one enantiomer are present in a quantity equal to those of the other enantiomer. This means that for every possible orientation of one enantiomer, which can cause rotation in a particular direction, say towards right, a molecule of the other enantiomer would be the mirror image orientation which would cause rotation in the opposite direction. Therefore, exact cancellation of all rotation would take place and the equimolar mixture would be optically inactive. The cancellation of rotation of one enantiomer by the other in an equimolar mixture of two enantiomer is known as external compensation, and the racemic mixture is said to be externally compensated. It may be pointed out that if the two enantiomers are not mixed in equimolar quantities, the rotation caused by one enantiomer is not exactly cancelled by the other. As such, this mixture still exhibits some optical activity. The direction of rotation corresponds to that of the enantiomer present in larger quantity, but the specific rotation is lesser. In this way, partial compensation takes place and the mixture formed is said to be partially racemized. Comparison of external and internal compensations. External compensation. This is due to the mirror image relationship between the structure of molecule of two enantiomer mixed together. Internal compensation is due to the mirror image relationship between the structure of two halves of the same molecule. In external compensation, the molecule of one enantiomer cancels the rotation of the other enantiomer, whereas in internal compensation, one half the molecule counterbalances the rotation of the other half. External compensation The racemate formed is the mixture of two isomeric compounds, whereas in internal compensation, meso and internally compensated compound represent a single pure compound. In external compensation, it is possible to have complete or partial external compensation of rotation so as to cause complete or partial racemization, whereas in internal compensation, partial internal compensation is not possible. In external compensation, it is a reversible process and the racemic mixture can be resolved into plus and minus enantiomer, whereas internal compensation is a permanent effect and it is not possible to resolve an internally compensated molecule into optically active form. Resolution of racemic mixture. The process of separating a racemic mixture into an enantiomer is called resolution. It is not easy to carry out resolution in actual practice. This is because enantiomers have identical physical and chemical properties which make their separation from each other very difficult. Therefore, special arrangement methods have been introduced for this purpose. First is mechanical separation. If the enantiomer of a substance exists in a well-defined crystalline form, the separation can be done by hand picking with the help of magnifying glass and a pair of pincers. For example, the enantiomer of sodium ammonium titrate can be separated by this method. Limitation. First, this method has very limited application as very few enantiomer substance exist in the form of mechanically separable crystal. Second is this method is very laborious and time consuming. Second is biochemical separation. This method involves the use of microorganisms for bringing about resolution. If certain bacteria, yeast or molds are allowed to grow in the dilute solution of a racemic modification, one of the enantiomer is selectively consumed by the microorganism while the other is left behind. For example, when the mold Penicillium gallium is allowed to grow in solution of racemic ammonium titrate, the mold completely destroys plus ammonium tartrate, while minus ammonium titrate is left practically unaffected. Limitation. First, the main disadvantage of this method is that one half of the material is destroyed during separation. Second, as the separation is carried out only in dilute solution, the process is very slow and only small amount of material can be separated. Third is chemical separation. This is probably the best method of resolution. It involves the conversion of racemic mixture into a mixture of diastereomers of some other substance by reaction with an optically active reagent. Since diastereomers have different physical properties, the mixture of diastereomers can be easily separated through fractional crystallization, fractional distillation, chromatography, etc. Each of the diastereomers is then suitably treated to generate a pure enantiomer of the original substance. For example, if a racemic mixture of plus and minus lactic acid is treated with a single enantiomer of an optically active base, say minus brucine, it would result in the formation of mixture of two crystalline salts. The two salts formed would be minus brucine plus lactate and minus brucine minus lactate. While brucine parts of these salts have the same configuration in both the cases, the acid part have non-superimposable mirror image configuration in two cases, so that the two salts represent two diastereomers. As such, the crystal of two salts differ in their solubilities and can be separated by fractional crystallization. Once the separation have been achieved, reaction of each salt with hydrochloric acid would generate free radical acid in pure enantiomeric form. Plus minus lactic acid plus minus brucine give rise to minus brucine plus lactate plus minus brucine minus lactate can be separated by fractional crystallization. Minus brucine plus lactate plus HCl give rise to plus lactic acid plus minus brucine minus HCl. Get crystallized, remain in the solution. Minus brucine minus lactate plus HCl give rise to minus lactic acid plus minus brucine HCl. Minus lactic acid get crystallized while minus brucine HCl remain in the solution. Apart from the separation of racemic acid or base. By this method, it can also be employed for the separation of racemic alcohol, aldehyde, etc. by treatment with suitable optical active reagent. Fourth is chromatography. These days, chromatography techniques such as adsorption chromatography using optically active absorbent, paper chromatography and gas chromatography are also being used for resolution. In adsorption chromatography, the solution of racemic mixture in the solution suitable solvent is passed through a column packed with optically active adsorbent when differential absorption of enantiomer take place. This is followed by elution with suitable solvent to get each enantiomer separately. Asymmetric or enantioselective synthesis. It have been already pointed out when a chiral compound is synthesized from a chiral compound, the product obtained is in the form of a racemic mixture. For example, propanoic acid in the presence of Br2 by P give rise to racemic mixture of plus and minus alpha bromopropanoic acid. The racemic mixture has then been resolved into the enantiomer through method described on previous pages. It is however found that if chiral compound is prepared from a chiral compound under the influence of some optically active substance which is subsequently removed, the product formed is optically active. This method of directly preparing an optically active isomer from a chiral molecule under the influence of some other optically active substance is called asymmetric or enantioselective synthesis. It may be pointed out that even in symmetrical synthesis, both the plus and minus enantiomer are formed, but one of these is obtained in predominating amount so that the product exhibits a net optical rotation. The following example illustrate the applicability of this process. First is the synthesis of minus lactic acid. Lactic acid obtained by the direct reduction of pyric acid as such is found to be in the form of racemic modification. However, if pyric acid is first esterified with an optically active alcohol such as minus methyl alcohol and the ester formed is subjected to reduction and then hydrolysis, we get a product having excess of minus lactic acid. Pyric acid plus minus methyl alcohol give rise to minus methyl pyruvate. Reduction give rise to minus methyl lactate. Hydrolysis give rise to minus lactic acid main product plus methyl alcohol. Second is synthesis of minus mandelic acid. Mandelic acid C6H5 single bond CH OH C double bond O single bond OH may be obtained in the racemic form by the reaction of benzaldehyde with hydrogen cyanide followed by hydrolysis. But when the same synthesis is carried out in the presence of an enzyme emulsin, like most other enzymes, it is optically active. Minus mandelic acid is formed to be the main product. Benzaldehyde in the presence of HCN give rise to mendelonitrile. Hydrolysis give rise to minus mandelic acid, main product obtained in the presence of emulsin. Most of the chiral compounds formed in the nature such as alkoxide and proteins are obtained in optically active form. This is because they are synthesized in nature under the influence of other optically active species. Prochilarity, prochiral atom. It has been shown above that the replacement of one of the hydrogen attached to C2 of the propanoic acid, which is optically inactive, by bromine give rise to racemic mixture of optically active product. This is because C2 is originally achiral in nature, but in the product form it becomes chiral. Such an atom is known as prochiral. A prochiral atom may be defined as the central atom in molecule, the replacement of one of the hydrogen atom attached to which by a substituent atom or group generates a chiral center. The molecule containing the prochiral atom is known as prochiral molecule and the phenomena is called prochirality. Propionic acid prochiral molecule replacement of H by Br give rise to racemic mixture of plus and minus bromopropanoic acid. Inversion of configuration, Weldon inversion. If an atom or group of atom directly attached to stereogenic center is substituted by some other atom or group, the configuration of new compound is sometimes found to be different from that of the original compound. This is known as inversion of configuration or optical inversion. This phenomenon was first discovered by Weldon and is therefore known as Weldon inversion. For example, first, when minus chloroseucine acid is treated with aqueous potassium hydroxide, the product obtained is plus malic acid having a different configuration than the starting compound. Minus chloroseucine acid in the presence of aqueous KOH give rise to plus malic acid, inversion of the configuration. Second is, when treated with aqueous KOH, minus 2-bromo-octane give plus 2-octanol, which has configuration opposite to that of minus 2-bromo-octane, that is minus 2-bromo-octane OH negative give rise to plus 2-octane, inversion of the configuration. It may be noted, however, that the change in configuration may or may not be accompanied by change in the direction of rotation. Retention of configuration, it is if the compound containing a stereogenic center is converted into another without breaking any of the bonds with the stereogenic center, the product has the same configuration as the original compound. This means that the reaction proceeds with retention of the configuration. For example, 3-bromo-2-hydroxy-propanoic acid in the presence of ZnHCl give rise to minus lactic acid of same configuration. Configuration and its specification. First is configuration. The arrangement in the space of atom or group constituting a stereoisomer is called its configuration. For example, the configuration of two enantiomer of lactic acid are 1 and 2 shown below. One of these configurations represent dextro or plus lactic acid while the other represent levio or minus lactic acid. Second is specification of configuration D and L notation. When we state that one of the enantiomer of lactic acid has the configuration first, while the other has the configuration second given above, we merely represent the two possible configuration of the enantiomer of lactic acid. What is not indicated in which configuration represent which enantiomer, it means which one of the two enantiomer plus or minus have the configuration 1 and which has the configuration second. In other words, we do not know the actual or absolute configuration of each of the two enantiomer. In the early days of the study of stereochemistry, it was found possible to determine the absolute configuration of the compound. Fortunately, it is also necessary to know that absolute configuration of an optically active compound. On the other hand, we are more interested in knowing the relative configuration of different compounds. For example, when an optically active compound undergo a chemical reaction, we are mainly interested in whether like configuration of the reactant and its product are same or different and not in their actual configurations. Relative configuration, standard reference compound. To assign relative configuration to various optical active compounds and to indicate their relationship, what was done was to choose a standard reference compound and fix its configuration arbitrarily. As proposed by Emil Fischer 1885, the compound chosen as standard was glyceraldehyde, CH2OH, CHO, HCHO, and its two enantiomer was designated by the symbol D, reads as D, and L, reads as L. It must be made clear that the symbol D and L refer to the configuration and are quite different from the prefix D and L, reads as dextro and levio, which refers to the direction of rotation. Plus glyceraldehyde was arbitrarily assigned to the configuration third, in which the minus OH group attached to the chiral carbon is towards right and was given the symbol D. The enantiomer was assigned the configuration fourth, in which the OH group attached to a chiral carbon is towards left and was given the symbol L. D plus glyceraldehyde and L minus glyceraldehyde. Three-dimensional and planar representation of two enantiomer of glyceraldehyde. Reason for selecting glyceraldehyde as the standard. Glyceraldehyde was chosen as the standard mainly because of the following reason. First, it is the simplest carbohydrate and aldotriose and its configuration could be easily related to those of the other carbohydrates which are stereochemically very important compound. Second is since glyceraldehyde contain very reactive functional group, it could be converted into many other type of compound. In this way, it could be configurationally related to large number of compound. Correlation of configuration. Many other compounds were then assigned relative configuration by relating their configuration to D and L glyceraldehyde. For this purpose, either the compound under examination is converted into D or L glyceraldehyde or D or L glyceraldehyde is converted into the given compound by means of the reaction which do not involve breaking of bond to a chiral center. The general principle involved in correlating the configuration of two compounds is that if a reaction does not involve the breaking of bond about a chiral center, the configuration about the stereogenic center remain unchanged. Some important examples of the correlation of the configuration are given below. First is minus glyceric acid can be obtained by the oxidation of D plus glyceraldehyde as shown below. Since this reaction does not involve breaking of bond about the stereogenic center, minus glyceric acid must have the same configuration as that of glyceraldehyde taken, it means D configuration. D plus glyceraldehyde oxidation in the presence of Br2 by H2O give rise to D minus glyceric acid. Second is the configuration of D lactic acid was established to the similar to that of L-glyceraldehyde by the following reaction. L-glyceraldehyde oxidation Br2 by H2O give rise to L-glyceric acid in the presence of phosphorus Br2 give rise to L plus 3 bromo 2 hydroxypropanoic acid, then reduction give rise to L plus lactic acid. Note of the reaction involving breaking of bond of the about the stereogenic center. Third, when D plus glyceraldehyde was converted into tartaric acid by the series of reactions shown below, a mixture of two products was obtained. These two products different from each other in their configuration around newly created stereogenic center marked asterisk. One of the product was the inactive or mesotartaric acid. Fifth, the other was the optically active tartaric acid which rotates the plane of light to the left. It means it was minus tartaric acid. Since it was obtained from D-glyceraldehyde by reaction which did not involve breaking of bond around the original chiral center, it was assigned D configuration. It means the same as that of starting glyceraldehyde. D-glyceraldehyde in the presence of HCN give rise to two configurations possible around new stereogenic center marked as asterisk. First is mesotartaric acid and second is D minus tartaric acid. Since D minus tartaric acid was assigned configuration 6, L plus tartaric acid would naturally have the mirror image configuration 7. D tartaric acid, L plus tartaric acid. It must be emphasized that there is no direct relationship between absolute configuration and the direction of rotation of polarized light. Two substances may have similar relative configurations and yet may rotate the plane of polarized light in different direction. For example, D plus glyceraldehyde and D minus glyceric acid have similar configuration even though the former is dextrorotatory while the later is levorotatory. D plus glyceraldehyde, D minus glyceric acid. Similarly, two compounds may have different configuration and even then they may rotate the plane of light in same direction. For example, D plus glyceraldehyde and L plus lactic acid have opposite configuration but the same sign of rotation. D plus glyceraldehyde, L plus lactic acid. Third is absolute configuration. It was only in 1951 that by using X-ray diffraction studies, Bijwit was able to determine the absolute configuration of compound. It means the actual arrangement in space of atom or group constituting a particular stereomers. The first compound whose absolute configuration was determined was sodium rubidium salt of plus tartaric acid. Bijvoet found that plus tartaric acid actually has the same configuration which it was previously assumed to have on the basis of configurational relationship between glyceraldehyde and tartaric acid as described above. If the assumed configuration of plus tartaric acid was correct, the assumed configuration of 2 enantiomer of glyceraldehyde must also be correct. As such, of the configuration of all other compounds derived by correlation with glyceraldehyde must be correct ones. Thus, the relative configuration assigned to D minus glyceric acid, L minus lactic acid discussed above, carbohydrate and a large number of other compounds actually represent their absolute configuration. The absolute configuration of some simple but stereochemically important compound are given below in the planar form. D plus glyceraldehyde, L minus glyceraldehyde, D minus lactic acid, L plus lactic acid, T minus tartaric acid, L plus tartaric acid. Fourth is limitation of D and L system of configuration. The system of designated the configuration as D and L is essentially based upon the configurational relationship to one or the other enantiomer of glyceraldehyde. But the procedure followed has certain limitation. It has been found that in some cases a given compound can be related by a sequence of reaction to a known compound having D configuration, but at the same time by another sequence of reaction the given compound can also be related to the L enantiomer of the non-compound. This leads to an ambiguous situation where the same compound may be assigned either D or L configuration. It may, however, be pointed out that in case of carbohydrate and amino acids, certain conventions have been adopted due to which the system of assigning D and L configuration is found very useful in these classes of compound. Rectus and sinister or R and S sequence for specification of configuration. In view of limitation of D and L system of configuration, Kohn, Ingold and Prelog suggest a very simple procedure to specify a particular configuration of system in terms of prefix R and S. The procedure involving the following two steps. Step 1. The 4 atom or group of atom bonded to a chiral center are assigned a sequence of priorities in accordance with a set of the rules known as sequence rule. Sequence rules. The sequence rules are as follows. Rule first. If all the 4 atoms directly attached to the chiral center are different from one another, sequence of priority is determined by their atomic number. The atom of highest atomic number gets the highest priority, while the one with the lower atomic number comes last in the order of priority. For example, in the compound 1-bromo, 1-chloroethane, the 4 group attached to the chiral carbon are CH3H, Cl and Br. The sequence of priority will be Br, Cl, CH3H. Similarly, the order of priority of the group CH3OH, NH2 and H is OH greater than NH2 greater than CH3 greater than H. If two isotope of same element are involved, the isotope with the higher mass number get higher priority. For example, out of the hydrogen H1N1 and deuterium H1N0, deuterium gets higher priority. Rule second. If the first atom of the 2 or more group attached to the chiral center have the same atomic number, the relative priorities may be fixed by comparing the next atom in the group. If even then does not solve the problem, the comparison may be extended further to the next atom and so on. For example, in the secondary butyl alcohol in relative priorities of CH3 and C2H5 are described as follows. Each of these groups is linked to the chiral center through the same atom carbon. The next atom is CH3 are HH and H, while in C2H5 they are carbon, hydrogen and hydrogen. Since carbon has the higher atomic number than hydrogen, C2H5s get higher priority than CH3. Therefore, the complete sequence of priority is OH greater than CH3 greater than CH2 greater than CH3 greater than H. Rule 3. If a group contains a double or triple bond between two atoms, it is treated as equivalent to the single bond or the three single bonds between the two atoms. In other words, each pi bond is supposed to be broken and other at the each end of the pi bond are duplicated. While doing so, two imaginary atoms are added for each pi bond broken. For instance, C double bond X is treated as equivalent to C single bond X attached with the carbon. X and C are imaginary atoms added due to the breaking of pi bond. Thus, it is considered that the group C double bond X contains two atoms of X attached to carbon. Similarly, single bond C triple bond Y is treated as equivalent to C attached with two imaginary Y and Y attached with two imaginary carbon. Therefore, the group single bond C triple bond Y is considered to contain three atoms of Y attached to carbon. To take a specific example in group single bond C, single bond H, double bond O, next atom to carbon are equivalent to oxygen, oxygen and hydrogen. That is, single bond C, single bond H, double bond O is treated as equivalent to single bond C, single bond H, single bond O, imaginary oxygen, single bond O, single bond imaginary carbon. It means there are two atoms of oxygen and one atom of hydrogen attached to carbon. Therefore, if we compare the group CHO and CH2OH, the former get higher priority as in the atom next to carbon are oxygen, oxygen and hydrogen, while in CH2OH they are oxygen, hydrogen and hydrogen. Comparison of the priorities of some typical group. Let us compare the relative priorities of vinyl, CH double bond CH2 and isopropyl group. In isopropyl group, the first carbon is attached to two carbon and a hydrogen. In vinyl group, also the first group carbon is treated as linked to the two carbon and the hydrogen. But in vinyl group, the secondary carbon is further attached to one carbon and the two hydrogen one of the other hydrogen. Is isopropyl, the second carbon is attached to only hydrogen, therefore vinyl group get priority over isopropyl group. Similarly, phenyl group get priority over acetylic group. Phenyl group is considered as if it has a Kekuli structure, that is, benzene treated as equivalence to. Acetylic group single bond C triple bond CH is equivalent to C attached with two imaginary carbon, then single bond C attached with two imaginary carbon, single bond hydrogen. In both, the first carbon is taken as attached to three carbon. In phenylic, two of the three carbon atom is attached to further first carbon and further attached to two carbon and hydrogen, while the third is duplicated carbon. In the acetylic group, only one of the three carbon attached to the first carbon is further attached to the two carbon and a hydrogen, while the other two are duplicated carbon. Therefore, phenyl group get priority over acetylic group. It is very evident that phenyl or acetylic group would get priority over vinyl or isopropyl group. This is because in phenyl or acetylic group, the first carbon is attached to three carbon, while in vinylic and isopropyl, the first carbon is attached to only two carbon. Thus, the order of priority of these groups would be C6H5 greater than single bond C triple bond CH greater than single bond CH double bond CH2 greater than isopropyl. Relative properties of some common groups. To sum up the above discussion on the determination of priorities of different groups, we give below the relative priorities of some common group on increasing order of priorities. Hydrogen CH3, CH3, CH2, then propane, CH2, double bond CH, then CH3 thrice carbon, CN, then OH CH2, then CHO, then CH3C double bond O, then OH C double bond O, then NH2, then OH, then CH3O, then fluorine, then SO3H, then Cl, then Br, then I. Step 2. Having decided the sequence of priority, the molecule is imagined to be positioned where the group of lower priority is directed away from us. Now we look at the arrangement of remaining group in descending order of their priorities, higher or number 1 downward. If it is doing so, the eye travel in clockwise direction. The configuration is specified as R. Latin rectus is equals to right. If on the right hand side the eye travel in anti-clockwise direction, the configuration is specified as S. Latin sinister is equals to left. Let us illustrate the above rules by considering some specific example. First is chloroiodomethane sulfonic acid. The sequence of decreasing priorities of the group attached to the stereogenic carbon: first I, second chlorine, third SO3H, and fourth is hydrogen. To assign configuration to it, the isomer shown below is held in the position so that hydrogen, which has the lowest priority, is pointed away from the observer. Now if the remaining group are arranged in order of decreasing priority, iodine, then chlorine, then SO3H, the eye has to travel in clockwise manner as shown ahead. Therefore, the configuration of this isomer is R. Proceeding in the same manner, the configuration of enantiomeric form of the above structure would be S. Second is lactic acid. CH3, CH, OH, C double bond O, single bond OH. The sequence of priority in decreasing order is OH, C double bond OH, CH3H. Therefore, the specific configuration of two enantiomers of the lactic acid may be designated as: first is clockwise, then R configuration, and second is anti-clockwise, then S configuration. Third example is 2-chlorobutane, CH3, single bond CHCl, single bond C2H5. The sequence of priorities is Cl, then C2H5, then CH3, then hydrogen. Therefore, specific configurations of its enantiomer may be given as: first is clockwise, then R, and second is anti-clockwise, so S. Configuration on the basis of projection formula. While assigning configuration to a stereoisomer on the basis of projection formula, two kinds of situation may arise. First, if the group of lower priority is bonded vertically, it means pointing away from the observer, the configuration is assigned by the following: exactly the same procedure as in the case of three-dimensional formula. For example, in the structure given below, the sequence of priorities is Cl, benzene, then CH double bond CH2, then hydrogen. The group of lowest priority is hydrogen is bonded vertically. It means pointing away from us. The moment of ice is moving from Cl to benzene to CH double bond CH2 is anti-clockwise. Therefore, the configuration is yes. If the group of lowest priority is bonded horizontally, it means pointing towards the observer. An additional step is required. In such cases, the given formula is converted into another equivalent projection formula by making two interchanges, so that the atom or group of the lower priority is placed vertically downward or upward. Then the configuration is assigned by the following done usual procedure. For example, second, assignment of configuration of the given isomer of 2-butanol. The sequence of priority is OH, CH2, CH3, CH3, then H. After the second interchange, hydrogen is bonded vertically in the projection formula. In moving from OH to CH2, CH3 to CH3, the eye travel in anti-clockwise direction. Therefore, configuration is S. Third is assignment of configuration to the given isomer of 2-aminopropanol. The sequence of priorities is NH2CHO CH3 hydrogen. Therefore, configuration is R. It may be recalled that if we carry out two interchange, the group attached to chiral carbon, the configuration remain equivalent to the original configuration. Configuration of compound containing more than one chiral center. In such cases, the configuration about each chiral center is
ascertained separately. The specification of each atom along with its number is then prefixed before the name of compound as illustrated below. First is, let us consider one of the form of tartaric acid given on the right hand side. Each chiral center carbon 2 and carbon 3 in this molecule has the same set of 4 group attached to it. It means C double bond OH, then hydrogen, then OH, and then CHOH, then attached to carboxylic acid. The sequence of priorities of these group is OH, carboxylic acid, CHOH, single bond C double bond OH, then hydrogen. The configuration around C2 may be assigned as follows. Since the I has to travel clockwise in moving from OH to C double bond OH to CHOH, C double bond OH, the configuration around C2 is R. Similarly, the configuration around C3 may be assigned as follows. It may be seen that configuration around C3 is also R. Thus, the configuration around each of the chiral center is S, so that the compound may be designated as 2R, 3R tartaric acid. Second is, let us now assign configuration to the compound. Each of the carbon atom 2 and 3 has the group CH3, hydrogen, Cl and CHCl, CH3 attached to it. The order of priorities of the group is Cl, CHCl, CH3, CH3H. Configuration at 2C can be known as follows. Configuration at C3 can be obtained as follows. Hence, the configuration of above compound is 2S and 3R. Useful shortcut for assigning configuration to Fischer projection formula. Decide the sequence of priorities of the 4 atom or group attached to the chiral carbon. Determine the configuration without making any interchange in the given projection formula. If the atom or group at lowest priority is bonded vertically, either upward or downward, in the projection formula, the configuration determined as above gives the actual configuration. If the atom or group of lowest priority is bonded horizontally either left or right, in the projection formula, change the configuration obtained above from R to S or vice versa to give the actual configuration. For example, without making any interchange, the configuration obtained is S. Since the atom at lowest priority, it means hydrogen is bonded vertically. This represents the actual configurational. Second is, without making any interchange, the configuration obtained is R. Since the atom of lowest priority, it means hydrogen is bonded horizontally. In the projection formula, change R to S. Third is, therefore, without making any interchange, the configuration obtained is S. Since the atom of lowest priority, it means hydrogen is bonded horizontally in the projection formula. Change S to R, therefore, actual configuration is R. Geometrical isomers hindered rotation around carbon-carbon double bond. First is geometrical isomerism and its case. Geometrical isomerism is a type of stereomerism which is exhibited by certain compound containing double bond and arise due to the hindered rotation about the double bond. We will first discuss geometrical isomerism in compound containing carbon-carbon double bond and then consider other type of compound which also exhibit geometrical isomerism. A carbon-carbon double bond consists of a sigma and a pi bond, while the sigma bond is formed by the overlapping of sp2 hybridized orbital of two carbon atoms along the internuclear axis. Pi bond is formed by the sideways overlapping of the unhybrid p orbital of the two carbon atom above and below the plane of atom. Because of this type of overlapping, rotation around carbon-carbon double bond is strongly hindered and can take place only if the pi bond breaks. But this would require about 284 kJ of energy per mole, which is not available to the molecule at room temperature. Due to the hindered rotation around carbon-carbon double bond, the relative position of group attached to the doubly bonded carbon atom get fixed. As a result, several higher alkene and other substituent product can exist in two distinct isomeric forms which differ from each other in the relative distribution of group in space around the double bond. For example, malic acid and fumaric acid afford a very well known example of compound which exist in geometrically isomeric form as shown below. Malic acid and fumaric acid. These two isomers are like one another with respect to which atom are attached to which other atom but differ from each other in the relative arrangement of atom in space. In malic acid, the two carboxylic group lie on the same side of the molecule, while in fumaric acid, the two carboxylic group lie on the opposite side. Such isomers which have the same structural formula but different in the relative spatial arrangement of group atom about the double bond are called geometrical isomerism, and the phenomena is known as geometrical isomerism. It is obvious that geometrical isomerism represents a type of stereoisomerism, since the stereoisomerism which are not mirror image of each other are called diastereomers. Geometrical isomers can also be regarded as diastereomers. It may also be pointed out that in case of optical and geometrical isomers, the different structure of the optical or geometrical isomer cannot be interconverted except by breaking or making of bond. As such, these two types of stereoisomers are also collectively known as configurational isomer. Condition for geometrical isomerism. There are two necessary conditions for a compound to exhibit geometrical isomerism. These are: first, the molecule must contain a carbon-carbon double bond, the rotation around which is strongly hindered. Second is each of the two doubly bonded atoms should have two unlike groups attached to it. For instance, ABC is equals to CAB. The formula APC is equals to CAB can have two arrangements in space which represent the geometrical isomerism as shown below. Similar group on same side of double bond, and second is similar group on the opposite side of double bond. For example, 2-butene exists in the form of geometrical isomerism as depicted below. Geometrical isomers of 2-butene. Sometimes the two groups attached to one doubly bonded carbon may be altogether different than those attached to the other carbon atoms, such as AB is equals to CCD. Even then, geometrical isomer would be exhibited. However, there is not an essential condition. Compound like propene and 2-methylpropene contain carbon-carbon double bond but still do not display geometrical isomerism. This is because one or both carbon involved in the formation of double bond carry two similar groups as shown below, propene and 2-methylpropene. No geometrical isomers possible. Nomenclature of geometrical isomers: cis and trans system. The method originally used for denoting the configuration of geometrical isomer is known as cis-trans system. In this system, the name of geometrical isomers having different configuration are distinguished by using the prefix cis, which means on the same side, or trans, which means across, before the name of compound. The prefix cis is used when similar groups are on the same side of the molecule, while the prefix trans is used when similar groups are on the opposite side, as illustrated below. Cis-2-butene, trans-2-butene. Cis-1,2-dichloroethane, trans-1,2-dichloroethane. Cis-1,2-dibromoethane, trans-1,2-dibromoethane. Malic acid cis, fumaric acid trans. Limitation of cis and trans system of nomenclature. The cis and trans system of nomenclature of geometrical isomer is not universally applicable. It can be employed in case of compound where all the four substituents attached to the two doubly bonded carbon atom are different from each other. A, B, C is equals to C, E, D. For example, let us consider the following compound.
Here we can see that I and Cl are cis to each other, but we can also equally well say that Br and Cl are trans to each other. Therefore, it becomes difficult to name such a substance either as cis or trans isomer. Fourth, E and Z system of nomenclature. In view of the limitations of cis and trans system, a more general system of nomenclature of geometrical isomers known as E and Z isomer is now being adopted. EZ system is based upon the sequence rule originally developed by Chan Prelog and Ingold For RNS system of specifying configuration of optical isomer, please refer to section on RNS system. For specifying the configuration of geometrical isomer as E or Z, the following rules are followed. First, the two atom or group attached to the each carbon of double bond are assigned a higher or lower priority according to the priority sequence rules of RNS system of optical isomer. If the higher priority atom or group on each carbon of double bond are on the same side, the configuration is designated as Z from the German zusammen is equals to together. On the other side, if the atom on the group of higher priority are on the opposite side, the configuration is termed as E from the German antigen is equals to across. Thus we have Z and E priority configuration. For example, Z 1 bromo, 2 chloro, 2 fluoro, 1 iodoethane. E 1 bromo, 2 chloro, 2 fluoro, 1 iodoethane. We know that atom having higher atomic number have higher priority. Therefore, out of F and Cl attached to C1 carbon, chlorine has higher priority. In the same way, out of bromine and iodine attached to C2, I has higher priority. Some more example of assigning E and Z designation are given below. Z 2 butane, E 2 butane. Z 3 chloro 2 methyl 2 propanoic acid, E 3 chloro 2 methyl 2 propanoic acid. Malic acid Z, fumaric acid E. It may be noted that most of the compound that we would normally designate cis are designated Z. Similarly, most of the compound that we would designate trans are designated E. Nomenclature of compound containing more than one double bond. If the compound contains two or more double bonds around which geometrical isomerism is possible, E and Z designations are given to each double bond. For example, 2Z, 4Z, 2,4 hexadiene, 2E, 4Z, 2,4 hexadiene. Similarly, 2Z, 4E, 2,4 hexadiene, 2E, 4E, 2,4 hexadiene. Determination of configuration of geometrical isomers. The following method can be employed for determining the configuration of geometrical isomers. First, from dipole moment. Determination of dipole moment of pair of geometrical isomerism can be quite helpful in designating a particular isomers as cis and trans. For instance, in case of compound of the type ABC is equals to CAB, the net dipole moment of trans isomer is expected to be 0. This is because the similar group are on the opposite side of the molecule and therefore the bond polarity cancel out each other. In contrast, the bond polarities are not cancelled in the case of cis isomer and therefore it has definite dipole moment. The cis 2 butenes should have a small dipole moment while the dipole moment of trans 2 butene should be 0. The following experimental data goes to support the above prediction. Cis 1,2 dichloroethane dipole moment is 1.85 diopter. Trans 1,2 dichloroethane is dipole moment is equals to 0. Cis 1,2 dibromoethane dipole moment is 1.35 diopter and trans 1,2 dibromoethane dipole moment is 0. Second is from boiling point. In general, cis isomer have higher boiling point than trans isomer. This is evidently because of the higher polarities and higher dipole moment of cis isomers, which lead to greater intermolecular attraction. For example, the boiling point of cis 2-butene is 277 Kelvin, while that of trans isomer is 274 Kelvin. Cis 2-butene boiling point is 277 Kelvin and trans 2-butene boiling point is 274 Kelvin. Third is from melting point. Generally speaking, trans isomer have higher melting point than cis compound. This is because trans isomers are more symmetrical and can be more closely packed in the crystal lattice. For example, malic acid cis melting point is 403 Kelvin, whereas fumaric acid trans melting point is 575 Kelvin. Fourth, from the formation of ring compound. Sometimes it is possible to distinguish between two geometric isomers by chemical reaction which lead to the formation of rings. Cis isomer is likely to undergo ring closure much more rapidly than the trans isomer. For example, malic acid cis form loses water when heated to 423 Kelvin to form malic anhydride ring compound. On the other hand, fumaric acid trans form does not give the anhydride at this temperature. Malic acid cis form at 423 Kelvin form malic anhydride ring compound, whereas it is fumaric acid at 423 Kelvin temperature gives no reaction. Fifth is biconversion into compound of non-configuration. Sometime a particular geometrical isomers can be converted into a compound of non-configuration without any change in the configuration around double bond. From the configuration of the product formed, the configuration of the starting compound can be deduced. For example, one of the geometrical isomer of trichlorocrotonic acid on hydrolysis yields fumaric acid while the other isomer does not. Since fumaric acid has a trans configuration, the isomer of trichlorocrotonic acid which changes into fumaric acid must also be the trans form. That is, trans trichlorocrotonic acid give rise to fumaric acid trans, and the other form of trichlorocrotonic acid does not give fumaric acid. 6 is from the formation of type of optical isomer. In certain reactions, geometrical isomers having carbon-carbon double bond change into product having newly created stereogenic centers. From the type of optical isomer formed, the cis or trans nature of the starting compound can be determined. For example, malic acid on hydroxylation with KMnO4 gives mesotartaric acid, while fumaric acid forms racemic mixture of tartaric acid as shown below. Malic acid cis form in the presence of KMnO4 give rise to mesotartaric acid, and fumaric acid transform give rise to racemic or plus minus tartaric acid. Seventh is geometrical isomerism in the compound other than alkenes. Geometrical isomerism can also be exhibited by compound in the molecule of which there may be hindered rotation due to some other reason than the presence of carbon-carbon double bond. Thus, geometrical isomerism is also shown by compound having carbon-nitrogen double bond, oxymin, nitrogen-nitrogen double bond, azo compound, and even some cyclic compound which do not contain any double bond as discussed below. First is geometrical isomerism in oximes. Oximes are the compound formed by the reaction between aldehyde or ketone and hydroxylamine. That is, aldehyde or ketone plus NH2OH give rise to C double bond NOH. For example, acetaldehyde plus NH2OH give rise to acetaldeoxime. Oxime exhibits geometrical isomerism due to the hindered rotation around carbon-nitrogen double bond, while the doubly bonded nitrogen carry only OH group attached to it. The doubly bonded carbon must have two unlike groups attached to it for geometrical isomerism to be possible. For example, geometrical isomers of acetaldeoxime. The configuration of geometrical isomers of oxime are usually denoted by prefix syn and anti instead of cis and trans respectively. In case of aldoximes, the isomer is named as syn if oxygen OH group attached to nitrogen is on the same side as attached to the carbon. If the OH group attached to the nitrogen is on the opposite side of hydrogen, the isomer is called anti. In case of ketoxime, the isomer is named as syn if the OH group attached to nitrogen is on the same side as the group attached to the carbon, which comes first in the name of the compound. If they are on the opposite side, the name is anti. For example, first is syn and second is anti-acetyl aldoximes. And in the second example, first is syn and the second is anti-ethyl methyl ketoxime. Determination of configuration of oxime. The actual configuration of geometrical isomers of aldoximes is determined by their relative ease of dehydration. When treated with dehydrating agents such as acetic anhydride and anti-aldoximes, undergo dehydration easily to form nitriles. For example, anti-aldoxime in the presence of AC twice oxygen give rise to nitrile. On the other hand, when a syn nitrile is treated with acetic anhydride followed by aqueous solution of sodium carbonate, original oxime is regenerated. The configuration of ketoxime are determined on the basis of Bachmann rearrangement when treated with an acidic reagent such as PCl5, P2O5 and SOCl2. The oxime undergo rearrangement to form a substituted amide. The structure of the amide thus formed helped to establish the configuration of the oxime. However, the detailed procedure would be discussed later. Second is geometrical isomerism in alicyclic compounds. There are many substituted alicyclic compounds which show geometrical isomerism. This is because the presence of a ring can also prevent rotation around carbon-carbon single bond. Therefore, geometrical isomer become possible if there are two carbon on ring, each of which is attached to two unlike groups. These two carbon may or may not be adjacent to each other. For example, dimethyl cyclopropane exists in two geometric forms. One in which the two methyl group are on the same side of the ring, and another in which they are opposite side of the ring as shown below. Cis dimethyl cyclopropane and trans dimethyl cyclopropane. Similarly, cyclobutane 1,3-dicarboxylic acid and cyclopentane 1,2-diol also exhibit geometrical isomerism. Cis-cyclobutane 1,2-dicarboxylic acid and trans-cyclobutane 1,2-dicarboxylic acid. Cis-cyclopentane 1,2-diol and trans-cyclopentane 1,2-diol. It may be pointed out that E and Z nomenclature is not used for cyclic compound. Conformations. It is well known that a single or sigma bond between two atoms is formed by overlapping of their orbitals along the internuclear axis. The electron distribution of the sigma bond thus formed is therefore symmetrical around the axis as shown in figure 2.12 for a single bond between sp3 hybridized orbital of two carbon atom. Due to its axial symmetry, the single bond allows freedom of rotation about it. As a result of this, the molecule of a compound can have different relative arrangements of their atom in space, which can be converted one into the other by the rotation around the single bond. Such arrangement in space of the atom in a molecule that can be readily interconverted by rotation around single bonds are called conformations and or conformational isomers. The existence of different conformation of compound constitute a special type of stereoisomerism. We will discuss some aspect of this phenomena with reference to alkane and cycloalkane. Figure 2.12 shows symmetrical electron distribution representing a single bond between sp3 hybridized orbital of two carbon atom. First is conformation of ethane. Ethane is the simplest molecule for which an infinite number of conformations are possible. The central bond in the molecule of ethane is a single bond between two carbon atoms, each of which is further linked to three hydrogen atoms. If one of the carbon atom of ethane is allowed to rotate around the central bond while the other is held still, a very large number of arrangements of the hydrogen of one carbon with respect to hydrogen of other carbon can be obtained. The basic structure of the molecule and various bond length and bond angle, however, remain the same in all these arrangements or conformations. Of the infinite number of possible conformations of ethane, two conformations represent the extremes. These are called eclipsed conformation and staggered conformation. In the eclipsed conformation, the hydrogen of one carbon are directly behind those of the other. In the staggered conformation, the hydrogen of two carbon atoms are staggered with respect to one another. Figure 2.13 and 2.14. Second is representation of conformations. Representation of conformation. Since it is not very convenient to represent three-dimensional formula on paper, certain conventions have been adopted for projecting the conformation on paper. The two commonly used methods are as follows. First is Sohor's formula or Enderian formula. In this representation, the molecule is viewed slightly from above and from the right and then projected on the paper. The bond between the two carbon atoms is drawn diagonally and of relatively greater length for the sake of clarity. The lower left hand carbon is taken as front carbon and the upper right hand carbon is as the back carbon. The three atoms or group attached to each carbon are shown tetrahedrally in space. The Sohor's representation are eclipsed and staggered conformations of ethane are shown in figure 2.13. Eclipsed and staggered. Figure 2.13 Sohor's representation of eclipsed and staggered conformation of ethane. Second is Newman projection formula. Newman devised a very simple method of projecting three-dimensional formula on paper, which are known as Newman projection. In these formula, the molecule is viewed from the front. The carbon atom nearer to the iris is represented by a point or dot, and the three atom or group are shown attached to it by three lines at an angle of 120 degree to each other. The carbon atom farther from the eye is represented by a circle and the three atom or group are shown attached to it by a shorter line, ending at the circumference of the circle at the angle of 120 degree to each other. Newman projection for eclipsed and staggered conformations of ethane is shown below in figure 2.14. First is eclipsed and second is staggered. Figure 2.14 is Newman projection for the conformation of ethane. Next is difference between conformation and configuration. First is conformation. As stated above, conformations are three-dimensional arrangement in space of atom in a molecule that can be interconverted merely by rotation around single bond. For example, figure 3.13 depicted two such arrangements known as eclipsed and staggered conformation of ethane, which are readily interconvertible by rotation around the carbon-carbon single bond. And the second is configuration. As already studied, configuration are three-dimensional arrangement in space of atom in a molecule that cannot be interconverted merely by rotation or about a bond. For example, the configuration of minus lactic acid and plus lactic acid, which are not interconvertible by rotation about the bond, are shown below in figure 2.15. Minus lactic acid and plus lactic acid, configuration of minus and plus lactic acid. In the light of above definition, the main point of difference between conformation and configuration may be summed up as follows. In the conformation isomerism, these are three-dimensional arrangement in the space of atom in a molecule which are interconvertible by rotation around a single bond, whereas configuration isomers as the three-dimensional rearrangement in the space of atom in a molecule which are not interconvertible by rotation around a bond. Second is their interconversion does not require any breaking and making of bond, whereas in configuration their interconversion is possible only through breaking and making of bond. Third is their existence leads to the phenomena of conformational isomerism, and the third difference of configuration is their existence is involved in the phenomena of geometrical and optical isomerism, which are also collectively known as configurational isomerism. Then fourth difference is, since conformation are readily interconvertible, they cannot be isolated from each other. As such, conformational isomer exist only as a mixture of different conformation, whereas since configuration are not easily interconvertible, they can be isolated from each other and stored as a pure substance. As such, configurational isomer can exist as pure individual substance. Conformational analysis of ethane. It has been stated earlier that a single bond allows freedom of rotation around it. However, it must be pointed out that rotation around a single bond is not completely free. If it were so, the potential energy for different conformation of a compound should have been the same, but in actual practice, the potential energy of the molecule changed somewhat with the rotation around the carbon single bond bond. The study of energy changes which occur in the molecule due to rotation around carbon single bond is known as conformational analysis. Let us first study the energy changes take place in ethane. The potential energy of the ethane molecule is minimum for staggered conformation, increases with rotation and become maximum for eclipsed conformation. The difference between the two extreme conformation being 12.55 kJ mole inverse figure 2.16. This difference in energy constitutes the energy barrier to rotation around the single bond. The energy barrier to the rotation in ethane is said to be due to the torsional strain, and the energy required to rotate the ethane molecule about the carbon-carbon bond is called torsional energy. The terms are explained a little later in section 2.24. Figure 2.6 shows change in potential energy during rotation about carbon single bond carbon of ethane. The energy barrier to rotation described above is, however, not large enough to prevent rotation altogether. Even at ordinary temperature, the molecule possesses sufficient thermal or kinetic energy to overcome the energy barrier through effective collision, and thus the conformation keep on changing from one to other. In other words, rotation around the single bond can still take place nearly freely, being only slightly restricted by the energy barrier. As such, it is not possible to separate different conformations of ethane. It is quite obvious, however, there is any movement, most of the ethane molecule would exist in the staggered conformation due to its minimum energy and therefore maximum stability. In other words, any molecule spends most of its time in staggered conformation, which is the most stable conformation. Next is conformational analysis of propane. If one of the hydrogen of ethane is replaced by another atom or group, the situation remains practically unchanged. For example, let us consider the case of propane, in which one of the hydrogen atom of ethane has been replaced by the methyl group. That is, in propane, rotation can take place about either of the two carbon-carbon bond. Even though the methyl group is considerably larger than the hydrogen, the energy difference between the two extreme conformation eclipsed and staggered is 13.8 kJ mole inverse, which is nearly the same as in the case of ethane. The most stable and preferred conformation is, of course, the staggered conformation, although it can almost freely change into the eclipsed conformation and vice versa. Figure 2.17 shows Newman projection for the conformations of propane. Next is conformational analysis of N-butane. The molecule of N-butane, which may be considered as distributed ethane, is somewhat more complex for conformational studies. If we consider the rotation only around the single bond between the two inner carbon atoms, C2 and C3 of N-butane, we have a molecule similar to ethane but with a bulkyl group. It means methyl group in place of hydrogen atom of each carbon. In contrast with ethene, N-butane can have several different staggered and eclipsed conformations due to the presence of methyl group. Four of the important conformations are anti-eclipsed, gauche and fully eclipsed. These are shown in figure 2.18. First is anti, then 60-degree rotation, second is eclipsed, then again 60-degree rotation, third configuration is gauge, and then again 60-degree rotation, fourth is fully eclipsed. 60-degree rotation, fifth is gauge, and then again 60-degree rotation, sixth is eclipsed. Figure 2.18 important configuration of N-butane. The anti-configuration first is an extreme staggered configuration in which the methyl group are far as apart as possible. If the angle of rotation around the C2 and C3 single bond is assumed to be 0, for this conformation and one of the C2 and C3 carbon atom is rotated through an angle of 60 degree, an eclipsed conformation second result. In this conformation, the methyl group attached to one carbon is not at the back of the methyl group attached to the other carbon, but it has the back of hydrogen attached to this carbon. Rotation by angle 60 degree leads to another staggered conformation called gauge conformation third, in which the two methyl group are only 60 degree apart. Further rotation by 60 degree gives rise to fully eclipsed conformation fourth, in which the two methyl group are at the back of each other. On further successive rotation by 60 degree, we pass through another gauge conformation fifth and another eclipsed conformation sixth, and finally arrive to the anti-conformation again on completion of 360 degree. The difference in the energy content between conformation first and fourth is about 18.4 kilojoule mole inverse, between first and second or sixth about 14.6 kilojoule mole inverse, and between first and third or fifth only about 3.8 kilojoule mole inverse, as shown in figure 2.19. The order of stabilities of different conformation of N-butane is anti greater than gauge, then greater than eclipsed, greater than fully eclipsed. It is apparent that due to very small difference in their energies, anti-conformation is only slightly more stable than gauge conformation. The difference is that in the energies of anti and gauge form is due to the steric strain, which is discussed in section 3.24. It can be easily seen that the rotation about the carbon-carbon single bond in N-butane is again nearly free, and the different conformation cannot be isolated. At any time, N-butane consists mainly of an equilibrium mixture of anti and gauge conformation, with the anti conformation having the highest percentage, about 67% at 295 Kelvin. It will be interesting to compare the spatial arrangement of two gauge conformation, third and fifth, of N-butane. It may be easily seen that these two conformers are also mirror image and hence enantiomer of each other. Such conformational isomers, which are also mirror image of each other, are known as conformational enantiomer. However, unlike configurational enantiomers, conformational isomers are very readily interconvertible by rotation around a bond. If we compare the anti-conformation first of N-butane with its gauge conformation third or fifth, it is found that first and third, or first and fourth, are not the mirror image of each other. Such pair of conformation are termed as conformational diastereomers. Thus, we found that conformational isomer can also exist as a pair of enantiomer or diastereomers, which however are readily interconvertible. Factor which influence conformational stability. Having discussed that rotation around single bond is not entirely free and the different conformation of a molecule have slightly different energy or stabilities, we would now consider the factor which influence conformational stability. First is torsional strain. This is the basic factor which influences the stability of a conformation. It is believed to be due to the interaction between the electron cloud of the bond attached to the central bond around which rotation is being studied. For instance, in the molecule of ethane, there are 6 carbon-hydrogen bonds attached to the central carbon-carbon bond. In the staggered conformation of ethane molecule, the electron cloud of these carbon-hydrogen bonds are as far apart as possible. But when the staggered conformation changed into the eclipsed conformation, these electron clouds rotate closest to each other. Naturally, there must be some repulsive interaction between the electron cloud in this position, which goes on to increase the energy of the molecule and thus decrease the stability. This repulsive interaction between the electron cloud affecting the stability of conformation is known as torsional strain. As a result of torsional strain, the energy of eclipsed conformation is more than that of staggered conformation, and consequently its stability is less.
The energy required for rotation around a single bond on account of torsional strain is called torsional energy. It constitutes the basic energy barrier to rotation about a single bond. In case of ethane, the entire difference in energy between the staggered and eclipsed conformations, it means 12.55 kJ mole inverse, is due to torsional energy or torsional strain. This is because no other factor affecting the energy or stability of conformation has any appreciable influence in this case. The situation is practically the same in propane. Second is steric strain due to van der Waals forces. When the hydrogen atom attached to the two singly bonded central carbon atom are replaced by a bulky atom or group, another factor called steric strain begins to influence the energy or stability of the different conformation. Steric strain arises out of the van der Waals forces of repulsion between the different parts of the same molecule. To understand their influence, let us go back to the molecule of N-butane. Here two hydrogen, one each of the two central carbon atom, have been replaced by the two bigger methyl group. These methyl group are farthest apart in case of anti-conformation of N-butane but are brought closer in the gauge and eclipsed conformations. Figure 3.19. Due to the crowding together of bulkyl group in these conformations, van der Waals forces of repulsion come into the play between these groups and cause a steric strain in the molecule. Due to this strain, the energy of the molecule increases and its stability decreases. Further instance, if we compare the anti and gauge conformation of N-butane, both are free of torsional strain due to their staggered nature, but gauge conformation is subjected to steric strain due to the nearness of their due to a nearness of methyl group which are only 60 degree apart, while the anti-conformation is free from their strain also. That is why the energy of gauge conformation is slightly 3.8 kJ mole inverse more than that of anti-conformation, and its stability is correspondingly less. If we consider the fully eclipsed conformation of N-butane, it is immediately obvious that both torsional and steric strain are operating to the maximum in this case. Accordingly, its energy is higher than that of anti-conformation, which is free of torsional strain as well as steric strain, but by as much as 18.4 kJ mole inverse, and its stability is least of all the conformations. It may be pointed out that the steric strain does not have any appreciable influence in the case of propane, as only one carbon atom carrier a methyl group. Ordinary van der Waals forces are considered to operate between the non-bonded atom of different molecules and are attractive in nature. But these forces can also operate between the different parts of the same molecule, and hence here the force can either attractive or repulsive depending upon the nature and size of group and their relative locations. Third is dipole-dipole interaction. In case of molecule having partially polar bond attached to the central single bond, dipole-dipole interaction can occur between the different parts of the same molecule. In the conformation in which positively charged poles are close together, the dipole-dipole interaction are attractive in nature and therefore have a stabilizing effect. On the other hand, in the conformation in which similar charged poles are brought together, these interactions are repulsive and therefore have a destabilizing effect. For example, if we consider the different conformation figure 2.20 of 1,2-dibromomethane, ethane, CH2Br, single bond CH2Br, it is evident that most stable and preferred conformation would be anti-conformation. This is because this conformation has practically no van der Waals repulsion between the bulkyl bromine atom as well as practically no dipole-dipole repulsion between the negative ends, it means bromine atoms of the polar bond. Figure 2.20 important conformation of dibromoethane. Fourth is angle strain. For sp3 hybridized carbon atom, the normal bond angle is 109 degree 28 minutes. Any deviation from the angle leads to an angle strain which makes the conformation less stable. This factor operates in case of cycloalkanes and other cyclic compound. This is discussed in the chapter of cycloalkane. Next is conformation of cyclohexane. We have so far studied the conformation of open chain compound. Let us now have a look at the conformation of cycloalkane by considering the case of cyclohexane. Cyclohexane is a multiplanar or puckered ring compound in which carbon atoms are in sp3 hybridized state and all the bond angle are equal to the normal tetrahedral angle. Of the various possible conformation of cyclohexane, the two more important conformations are: first is chain conformation and second is bond conformation. First is chain conformation. This is most stable and therefore the most preferred conformation of cyclohexane. In this conformation, all the bond angle are tetrahedral and all the carbon-hydrogen bond on adjacent carbon atom are in staggered position. Figure 2.21. At the same time, there is no steric interference or dipole-dipole interaction between the non-bonded atom. Thus, this conformation is essentially free of strain and has minimum energy. In other words, this is most stable conformation of cyclohexane. Second is bond conformation. This is the second most important conformation of cyclohexane and is depicted in figure 2.22. As in the chain conformation, there is no angle strain in the bond conformation since all the bond angle in it are tetrahedral, but in bond conformation, the hydrogen on 4 of the carbon C2 and C3, C5 and C6 are eclipsed. As a result, there is considerable torsional strain. At the same time, the two hydrogen pointing towards each other at C1 and C4, known as flagpole hydrogens, are very close together, the distance between them being only 183 picometer and 1.83 angstrom, while the sum of their van der Waals radii is 250 picometer and 2.5 angstrom. This gives rise to van der Waals strain also in the molecule. Due to the torsional and van der Waals strain in it, the bond conformation is naturally much less stable by 28.8 kJ mole inverse than the chain conformation. As such, only very few molecules of cyclohexane, only one in about 1000 at room temperature, exist in bond conformation. Other conformation. In addition to chair and bond form of cyclohexane, several other conformations are also possible as discussed below. Third is twist bond or skew bond conformation. Let us consider a model of bond conformation of cyclohexane as shown in figure 2.323a. Suppose we hold C2 and C3 in one hand and C4 and C5 in the other and twist the molecule so that C3 and 6 go down while C2 and C5 come up. It will notice that during this twisting, the flagpole hydrogen on C1 and C4 marked HA and HB in the figure move apart, and at the same time two hydrogen on C3 and C6 marked HC and HD in the figure begin to move close together. In this way, we get another conformation called twist bond or screw bond conformation, in which the distance between HA and HB is equal to that between HC and HD. It is quite evident that in this conformation, the van der Waals strain between flagpole hydrogen is minimum. At the same time, the torsional strain on C2 and C3, C5 and C6 also appreciably reduced. As such, the twist bond conformation is more stable than the bond conformation by about 6.7 kJ mole inverse, although it is still less stable than chair conformation by 23 kJ mole inverse. Fourth is half chair conformation. In between the chair conformation and twist bond conformation lies yet another conformation known as half chair conformation, figure 2.24. It has both an angle and torsional strain and thus has about 46 kJ mole inverse higher energy than chair form. In fact, it represents merely a transition state conformation.
Energy relationship between different conformations. The energy relationship between the different conformations of cyclohexane have been shown in figure 2.25. It must be pointed out that the energy difference between any two conformations is too small to permit this isolation. It is evident that the order of relative stabilities of different conformations of cyclohexane is chair conformation greater than twist bond conformation greater than bond conformation greater than half chair conformation. Equatorial and axial bond in cyclohexane. Since the chair conformation is the most preferred and the most important conformation of cyclohexane, let us examine it little more closely. Although the cyclohexane ring is not flat, we can imagine an average or general plane of the ring. Now if we consider the position of various hydrogen atoms in the chair conformation, we find that there are two different kinds of hydrogen. 6 of the hydrogen marked He in figure 2.26 point sideways along the general plane of the ring and are called equatorial hydrogen because they are situated along the general plane of equatorial belt of the molecule. The other 6 hydrogen marked Ha in two groups of 3 each lie above or below the general plane and point along an axis perpendicular to the ring. These are known as axial hydrogen. The bond by which an equatorial hydrogen is held is called an equatorial bond, and the bond by which the axial hydrogen is held is called axial bond. There is one equatorial and one axial bond on each carbon in the chair conformation of cyclohexane. It may be pointed out that the distance between hydrogen on adjacent carbon atom in cyclohexane is 230 picometer or 2.3 angstrom, which is same as in staggered ethane. However, axial hydrogens on the same side of the molecule are situated rather close together even though they are linked to alternate carbon atom, but it may be noted that the distance between such hydrogen is also 230 picometer or 2.3 angstrom. It is interesting to note that the axial and equatorial hydrogen in cyclohexane can interchange their position. This is because the chair conformation of cyclohexane is flexible and one chair conformation can change into another chair conformation by process known as ring conversion, ring flipping. As this happens, all hydrogen originally axial become equatorial and vice versa. But one chair conformation is perfectly equivalent to the other and they cannot be distinguished from each other. Conformations of monosubstituted cyclohexane derivative. As the two bonds on each carbon of cyclohexane ring are not equivalent in position, a monosubstituted cyclohexane derivative should exist in two isomeric form according as the substituent group is in an equatorial or axial position. Such equatorial and axial conformation of substituted cyclohexane can interconvert into each at room temperature by ring flipping, but they are not equivalent to each other in energy. The conformation having the substituent in energy equatorial position has slightly lesser energy than the other and is somewhat more stable. The reason for this can be understood by constructing their model. It can be seen from the models that substitution of the axial hydrogen by the bigger atom or group led to the considerable crowding between this substituent and the two axial hydrogen on the same side of the molecule. The interaction resulting from such crowding of axial atom or grouping is called 1,3 diaxial interaction. To illustrate the operation of such interaction, let us consider methyl cyclohexane. Figure 2.27 shows the two possible chair conformations of methyl cyclohexane, one having the methyl group in an axial position, figure 2.27a, and the other having this group on equatorial position, figure 2.27b. It can be seen, figure 2.27a, that one of the hydrogen of axial methyl group on C1 is very close to the axial hydrogen on C3 and C5, but there is no such sufficient crowding when the methyl group in equatorial position, figure 2.27b. In other words, axial methyl group is more crowded than the equatorial methyl. The resulting 1,3 diaxial interaction is responsible for the lesser stability of axial conformation than the equatorial conformation, the difference in the relative stabilities of the two being 7.5 kJ mole inverse. Since the difference of 7.5 kJ mole inverse of energy between the axial and equatorial conformation of methyl cyclohexane is due to 1,3 diaxial interaction between one methyl group and two hydrogen, it is reasonable to expect that 1,3 diaxial interaction between each axial hydrogen and methyl group led to difference of 3.75 kJ mole inverse. This can enable us to predict the relative stabilities of the various conformations of substituted cycloalkanes having more than one methyl group. As stated above, the equatorial methyl cyclohexane and axial methyl cyclohexane can interconverted into each other readily and exist in equilibrium with each other but at room temperature. 90% of the molecule of methyl cyclohexane are those having axial methyl group. This is apparently due to lesser energy or greater stability in case of equatorial methyl group. Conversion of Fischer projection formula into Sohor's formula and Newman's projection formula. In conclusion of the discussion on stereochemistry of organic compound, we may point out an interesting drawback of Fischer projection formula of diastereomers having two chiral carbon atom. The Fischer projection formula of such compound correspond to the less stability eclipse conformation involving maximum crowding between the substituent group attached to the two chiral carbon atom. But actually the molecule acquire the shape which correspond to the staggered form in which the substituent are as far apart from each other as possible. Therefore, the best way of representing such molecule is to depict them in their staggered form by means of Sohor's formula or Newman's projection formula as explained below. First is conversion of Fischer projection formula into Sohor's formula. This involves two steps as given below. First is write the Fischer projection formula and change it into equivalent eclipsed representation in the term of Sohor's formula. Second is rotate one of the chiral carbon atom by an angle of 180 degree around the bond between the two chiral carbon to get the Sohor's representation to be staggered form. For example, let us convert 2s3r 3-bromobutane 2-ol from Fischer projection formula to Sohor's formula. Second is the conversion of Fischer projection formula into the Newman projection formula. This also involves a similar procedure in which the Fischer projection formula is first translated into the equivalent eclipsed form in terms of Newman's projection formula. The latter is then changed into the staggered form by rotating through an angle of 180 degree around the bond angle of the two chiral carbon. For example, 2s3r 3-bromobutane 2-ol converted into Newman projection. Thank you.